Good afternoon. My name is Thomas Tucker. I am an engineer within my organization's IP engineering group, and this module is going to cover configuring a VPRN on the Nokia 7750 SR platform. And we're going to assume that the reader's familiar with the service architecture of SROS, as well as LDP, MPLS, IGPs, and EGPs. Just a basic understanding of BGPs required. And the RFC for this module is going to be 4364, BGP, MPLS, IP VPNs. So if required, just pause the presentation, take a few minutes and review the service architecture for SROS. All right, so here's our logical view of the VPRN service. And note that we have 3 VPRNs configured on router N1, VPRN 1112 for subscriber A, 2233 for subscriber B, and 3344 for subscriber C. And we're going to focus mainly on subscriber C, or VPRN 3344, simply because this particular subscriber has a site that's connected to each provider edge router. So the concept that applies to subscriber C is also going to apply to subscribers A and B. But the thing to notice about all the subscribers in general is that although they connect to different SAPs on the PE router, they're all going to share the same addressing scheme. So within each particular VPRN on the PE router, our interface is going to be numbered, for example, on N1, 192.168.1.0 for our SAP, and then the other end of that point-to-point is going to be .1 that we configure on our CPE. So once we have this interconnect established from our customer edge router to our provider edge router, we're also going to be configuring a service distribution point or a full mesh of service distribution points, just like in VPLS, between our provider edge routers. And we're going to be exchanging labels through those service tunnels, but instead of using targeted LDP to generate those service labels, we're going to be using BGP labeled unicast to generate those service labels. And that label information is going to be exchanged instead of using LDP or targeted LDP. It's going to be exchanged in update messages using multi-protocol BGP. All right, so taking a closer look at subscriber C's network, and technically this wouldn't be subscriber C's network. It would more or less be subscriber C's routing domain. And that's an important concept to keep in mind. Simply when we remember, for example, our virtual private wire service was creating a collision domain or a single layer 2 circuit between R1 and R2, then our VPLS service was creating a single broadcast domain between each of the routers, or each of the customers stubbed off of each router, R1, R2, and R3. So our VPRN service is essentially going to let us interconnect separate broadcast domains into a single routing domain. So the service provider IP MPLS core in the middle here is going to act as a virtual router. So when our CPE is plugged into the provider edge router, then these public /24 networks, like the 151 network in Los Angeles, the 98 network in New York, and the 24 network in Dallas, these separate broadcast domains, I should say, are going to be able to communicate with each other through the service provider. So from each site's perspective, they're going to be plugged into a single router. And here are some of our VPRN components. All of them are important, so pause the slide and review them, as well as the RFCs. All right, so continuing with our VPRN components, these are sort of the three uh, moving pieces, more or less, or the pieces that do the heavy lifting for VPRN, and that's the CE to PE routing, PE to PE routing, and PE to CE routing. So the CE to PE routing is where the router peers with, or the customer edge router peers with and distributes routes to the local PE router. PE to PE routing is when the customer's routes are distributed to the other PE routers using multi-protocol BGP. And then PE to CE routing is when the routes learned from other PE routers are distributed to the local customer network. So really any IGP can be used to exchange routes between the customer edge and the provider edge. More commonly, you'll see BGP4 being used. So that's what we're going to use in our lab. Um, so since we're using BGP4, we know that the prefixes are exchanged or distributed, I should say, in update messages. So we're just going to pretend that this gray arrow is our update message. This is the update message that's going from our customer edge router to our provider edge router. And it just contains the /24 prefix, our public /24. So once it gets to the provider edge router, notice that previously we said that the provider edge router was running multi-protocol BGP between each other provider edge router. So once the PE router receives this update message, uh, depending on what SAP it came in on, it's going to distinguish this route within the service provider network by attaching a route distinguisher to it, which in our case is going to be 65,000:3344. It's then going to generate a label for this particular IPv4 prefix, and this is going to be called our VPN label. And in our case, the label 3344 is generated. And finally, it's going to attach an extended community onto this update message, which in our case is going to be the route target 65,000:3344. So the actions that the provider edge router take on this particular prefix is first, it's going to generate a VPN label for this prefix because it has to store this prefix in its VPN table. And the VPN table is shared between all of the provider edge routers. So it needs a way to distinguish this particular IPv4 prefix. So it does that by prepending it with the route distinguisher, thus creating our VPN v4 prefix. And once the VPN v4 prefix is created, uh, then multi-protocol BGP will attach a route target onto it. And that route target is going to instruct the PE router which routing table to place this VPN v4 prefix in. So once N6 receives this update message, again, and it accepts the prefix because it's distinguishable from every other prefix in the service provider network, given that it has a unique route distinguisher. So based on the VPN label, router N6 is able to tell what the IPv4 prefix should be, which in our case is just 151.41. That really should be .42, .1.0, but we'll change that. With the label 3344, or from the label 3344, my apologies. It's able to tell what this IPv4 prefix should be, and based on the route target, it's able to tell what particular VPRN this IPv4 prefix belongs to. So let's just pause it and fix this. If I don't do it now, it'll never get done. All right, so now it makes sense. So just going back to Subscriber C's network, technically Subscriber C's routing domain. Um, their site in Los Angeles has the public IP block of 151.42.1.0/24, and that's what's being distributed to the provider edge in this example. All right, so the prefix comes from the CPE to the PE in an update message. The PE generates a label for the prefix and prepends it with a route distinguisher, then attaches a route target to it and sends it to the far end provider edge or the egress label edge router. And the egress label edge router, based on the VPN label, tells what the IPv4 prefix is, and based on the route target, chooses the VPRN or VPRNs to install that route into. And then finally, based on routing policy, and this is because, again, we're running BGP4 between the as our CE to PE protocol and as our PE to CE protocol. So based on our routing policy, we're going to instruct router N6 to take these VPN v4 routes out of the BGP VPN table and install them into the BGP table. And once they're installed in the BGP table, they'll then be redistributed from our egress label edge router to the far end CPE. And they should be installed into the BGP table if everything goes accordingly. All right, so this slide by now should look very familiar. It's the same slide I've used in the services architecture, the VPWS, and the VPLS video. And it's just to drive home the point that these services, uh, in a certain way, all behave exactly the same, in the sense that uh, we have data getting from one customer site, in this case R1, to a different customer site on R2. That customer payload is going to ingress a particular service access point on the PE router. And based on that service access point, that data is going to be multiplexed or encapsulated with a service label. In the case of our VPRN, it's going to be a VPN label. But then based on the egress label edge router, that datagram is going to be further multiplexed or label stacked with a transport label. And then, forwarded out our egress interface. And that datagram is then going to be label switched all the way to our egress label edge router, where the service or VPN label is going to be read, and that packet is going to be processed and egressed out the appropriate set. So it behaved that way with our virtual private wire service. It behaved that way with our virtual private LAN service, and it behaves that way as well with our virtual private router network. That being the overall way a customer payload goes from site A to site B. All right, so we'll start looking at our configuration, and let's just open our, we've got our project open already, so we're just going to start it. And while our devices are booting, we'll take a look at the configuration that we're going to put on these routers. Let's just make sure the Nokia routers are booted properly. All right, that was good. All right, so um, this particular order of operation, this is just what I do in particular when I build a VPRN. It's just what's easiest for me and what makes sense to me. But you know, whatever is easiest for you and whatever makes sense to you is what you should definitely do. This is just one example of how I typically build VPRNs. So first, I start with the policy that's going to redistribute the routes from our egress label edge router's uh, BGP VPN table to its VPRN's BGP table. And that's going to start, first we have to enter the policy options edit mode. So we do that with the command configure router policy options begin. And we're going to name this policy statement multi-protocol BGP to BGP. And our default action is going to be reject. And for our first entry, entry 1, we're going to take routes from, again, the routing table BGP VPN, place them in or to protocol BGP, the BGP4 table, and our action is going to be accept. And once we've got our policy built, we're going to commit it with the command uh, / because at this point we'll still be in the policy statements context. So / configure router policy options commit. And once we have our routing policy built on each provider edge router, I then like to build our service distribution points, which are going to be our targeted LDP sessions. So configure service enters the service context, and we're going to create 2 service distribution points. And keep in mind that this is from the perspective of router N1. So we're going to have one service distribution point to router N6 and another service distribution point to router N7. And since this is going to be a full mesh of service distribution points, on router N6, we're going to have one to router N1 as well as router N7. And on router N7, we're going to have a service distribution point to router N1 as well as a service distribution point to router N6. So configure service enter the service context, SDP 17006 MPLS create. That's going to create our service distribution point and specify MPLS as the transport type. And I've been getting more than a few questions on this, particularly someone sent me a message to the effect of if you don't have MPLS configured on your interfaces, why is your traffic being label switched? Or I don't have MPLS configured on my interfaces. I'm trying to use GRE, so why is my traffic label switched or being label switched? So he sent me his configuration, and I pointed out that in the configuration for his service distribution point, he was using MPLS or specifying MPLS as the transport type. So if for whatever reason you wanted to use GRE as your transport type, then here's where you would specify that. So for example, if we wanted to use GRE for this SDP's transport, our command would be SDP 17006 GRE create. And that's it. But in our network, we're going to be using MPLS. So within each service distribution point, we're going to specify the far end. In the case of 17,006, our far end is going to be N6. And in the case of 17,007, our far end is going to be N7. But we're going to instruct each service distribution point, as always, to use LDP signaled LSPs. All right, so continuing the VPRN configuration, and this is from the perspective of router N1. This is our CE to PE config. The first thing we're going to do is create the customer. Then we're going to create the service. And once we've got our service created, we create we configure rather, the ASN, route distinguisher, and route target. And typically I'll also configure the router ID just out of habit and just as a best practice. But once we've got a bit of our routing configured, we go ahead and create and bind our service access point. And again, on N1, we're going to address this 192.168.1.0/31. And we're going to bind it to the physical port 115 with a service delimiting VLAN tag of 42. And at this point, we should have layer 3 connectivity between our provider edge and our customer edge. So you could do a ping test, but the router will now be, well, Cisco calls it VRF aware. So if you wanted to ping this particular host, since the router now recognizes this VPRN as router 3344, your command would be ping router 3344 192.168.1.1, and source it with a .0. Or if you wanted to look at the global routing table, for example, your command would be show router route table. But if you wanted to look at this particular VPRN's routing table, your command would be show router 3344 route table. So once we've got our layer 3 connectivity established, we can go ahead and configure our CE to PE protocol. And as we said earlier, this is going to be BGP4. So as a best practice, we've created a BGP group, and we're going to apply our routing policy or our policy statement as an export policy to this BGP group. And our peer AS is going to be 65,001. So this is going to be an external BGP4 neighborship since our local AS is 65,000. And then we specify our neighbor 192.168.1.1. And finally, we go ahead and bind our service distribution point to the service with the command spoke SDP 17006 create. So we're going to bind our service distribution point to router N6 as well as router N7 to this particular service. And here we have our PE to PE routing protocol. So first we configure our local ASN, and we've arbitrarily chosen the ASN 7029, just any public ASN to represent a particular service provider. And once we've got the ASN configured, we configure a BGP group. So configure router BGP group, multi-protocol BGP peers. And this is when we enable multi-protocol BGP. We specify the VPN v4 address family with the command family VPN-IPv4. And we specify the peer AS 7029 as well as our neighbors, which is going to be router N6 and N7. And since our peer AS matches our local AS, these will be internal multi-protocol BGP neighborships. And finally, configuring the PE to CE interfaces and protocol. And it's going to be the exact same as it was on router N1, except on router N6. We're using a different network for our ISP interconnect. We're using the 192.168.2.0 network. And our peer AS for the site that's built on router R2 is going to be 65,002. But again, we're going to specify 2 spoke SDPs from router N6. One is going to be to router N1, 17,001, and the other is going to be to router N7, 17,007. So here's the VPRN design in tables. I figured it'd be probably a little bit easier to visualize. So we're only going to be focusing on the VRF and the VPRN 3344. And I've highlighted each of the subscribers' public IPv4 blocks that we need to make reachable uh, through our VPRN. But again, as you can see, each subscriber's interface is going to share the exact same IP scheme. And on our provider edge routers, each VPRN is going to go as far as to share the same ASN as well. All right, so this monstrosity is a logical view of what our routing is going to look like. So within our service provider IP MPLS core, we have our label switch routers all in ISIS area 49.0.0. So routers N1, N2, N3, 4, 5, 6, and N7. And we're running external BGP4 between our provider edge routers and our customer edge routers. And we're also running multi-protocol BGP between each of our provider edge routers. So this neighborship you see at the top, multi-protocol BGP, AS7029 to AS7029. This is a full mesh, but I mean, there's only so much mess you can fit on one PowerPoint slide. So just envision another multi-protocol BGP neighborship from N1 to N7 and from N7 to N6, because we're going to have that full mesh. All right, so our goals, and let's just make sure our routers are good to go. Good so far. We might as well just organize our CPEs and our switches. All right, so admin, of course, is always the default username and password for SROS. We're just going to go ahead and log into our PE routers here. And what we'll do as well is we'll go ahead and, well, no, we'll wait on that. Do this one thing at a time. So configure routing policy on each PE in N1, N6, and N7 that will allow routes to be redistributed from multi-protocol BGP into BGP4. Go back to our slide. You see we're going to configure a policy statement whose default action is going to be reject. And for our entry, we're just going to specify from protocol BGP VPN to protocol multi-BGP. Excuse me. And commit that policy. So nothing fancy. So configure router policy options. Begin puts us in edit mode. And we're going to take it one step beyond. All right, so when we form these BGP neighborships, we're going to be redistributing not only our public /24 blocks, but also our ISP's interconnects, which is going to be the private space. So just to keep our routing tables a little bit cleaner, we're going to create a prefix list that's only going to allow our public /24s to be redistributed to our CPEs. So our private addressing won't make it to our CPEs. So let's create a prefix list, and let's call it VPRN 3344 sites. And you specify the first prefix, which is going to be our public /24 in Los Angeles. So 151.42.1.0/24. Exact. Next, we're going to specify the block in New York. 98.98.98.0/24 exact. And finally, our block in Dallas, I believe it was 24.137.88.0. All right, now we're going to go ahead and make our policy statement. Multi-protocol BGP to BGP4. Specify our default action, which is going to be reject. Create entry 1, and we're going to instruct it from the prefix list, VPRN 3344 sites. So only these prefixes are going to be allowed to be redistributed from the multi-protocol BGP table to the BGP table. So from prefix list VPRN 3344 sites, from protocol BGP VPN to protocol BGP. Of course, our action is going to be to accept. All right. So just going over our routing policy one more time. If a prefix is any of these within our prefix list, and it's in our BGP VPN table, then we're going to accept those prefixes into our BGP table. So once this looks good, we're going to go ahead and commit instead of comment. And we're going to do that on each of our provider edge routers. So on router N6, configure router policy options, begin. Prefix list, VPRN 3344 sites. We're going to do our prefixes. That's Los Angeles. This is LA. I mean, that was LA. This is New York. And this is Dallas. And create our policy statement for multi-protocol BGP to BGP4. Specify our default action of reject. Entry 1, we're going to take prefixes from our prefix list. VPRN 3344 sites. And from protocol BGP VPN to protocol BGP. As always, our action is going to be to accept. Let's do the same thing on router 7 here. Configure router policy options, begin. Prefix list, VPN 3344 sites. Prefix, this is going to be Los Angeles. This is going to be New York. And this is going to be Dallas. And we're going to make our policy statement to redistribute our routes from multi-protocol BGP into BGP4. Specify our default action of reject. Entry 1 from prefix list, VPRN 34 sites, and from protocol BGP VPN to protocol BGP. And our action is going to be to accept. Once we commit that, we're going to go ahead and save the configuration. All right, so we've got our routing policy out of the way. Next, we're going to configure a full mesh of service distribution points or targeted LDP tunnels between the provider edges. All right, so on router N1, we're going to have a service distribution point to router N7, as well as one to router N6. And then on router N6, of course, we're going to have one to router N7. So this is going to be full mesh of SDPs. So configure service. First, we'll create the one that's going to router N6. So 17006. Specify the transport type MPLS. Question mark here so you can see. The transport type or delivery type that you can specify MPLS GRE or L2TPV3. So we're going to be using MPLS. The far end is going to be router N6, and we're going to be using LDP signaled LSPs. And we're going to create the SDP to router N7, 17007. Specify the far end router N7 and LDP. And as expected, well, we have a opera tunnel to N7, but not one to N6. So let's check N7. Let's make sure that N1 can reach N6. Yep, that will explain it. So let's see which of our routers didn't boot properly. Look at our ISIS routes. They've got routes for router 2, router 3, and router 7. So let's see the router 4 and router 5. Where is? Let's get those rebooted. All right, so while those are booting, we'll go ahead and finish building our other SDPs. So on router N7, we're going to have service distribution points to router N1 and N6, 17001 and 17006. So router N7, configure service, SDP 17001, MPLS create. The far end is going to be router N1. And SDP 17006, MPLS create. The far end is going to be router N6. And on router N6, we're going to have service distribution points to router N1 and N7. So configure service, SDP 17001 create. Sorry. Far end is going to be router N1. Our other SDP 17007, MPLS create. Our far end is going to be router N7. I'm going to go ahead and save that config. See how routers N4 and N5 are doing. They're taking their time. All right. Let's see how much time we have left before these reboot. 40 minutes. Oh, we're golden. All right, so we've got our full mesh of SDPs. I guess we can verify that they're up. So they're both up or up. So now we've got to configure our CE to PE routing. So configure each CE to distribute a public IPv4 system address to the PE via external BGP. Very importantly, each address must be in a separate broadcast domain. And we're also going to configure a VPRN service for the subscriber. In our lab, it's going to be subscriber C on each PE. So let's go ahead and take care of these customer edge routers. And the first thing we're going to do is we're going to enable VLAN 42, since that's subscriber C's VLAN, on switch 1, switch 2, and switch 3. We've got our trunk ports configured already, but we've just got to allow that particular VLAN through these trunk ports. So very quickly on each switch, conf T VLAN 42. Close that. Switch 3, conf T VLAN 42. All right, so we'll start with R1. Just take a look at our IP interfaces. If you've been following along with us, we have our interface for our VPWS and our MPLS. So now let's create the interfaces for our VPRN. And looking at our design, you see we're going to have gig 00.42 is going to be 192.168.1.1/31. And loopback 42 is going to be the gateway or the .1 address for this /24 network. 151.42.1.1/24. So these aren't Cisco modules, so we're not going to go into how to do this on iOS, but we are going to just talk through it. So first we're going to define the VRF, which in our case is going to be VRF 3344. Our route distinguisher is going to be 65,001:3344. 1 second. Excuse me. All right, and now we're going to configure our route target. 65,001 colon, specify both for import and export. 65,001:3344. All right, and with that, our VRF is built. All right, so now we're going to go ahead and add our interfaces into the VRF. First is going to be our ISP interconnect. And we're going to give it the IP address 192.168.1.1/31. First, you've got to specify encapsulation.1Q42. Then we throw on our IP address. And also we're going to configure our public /24's gateway. So we're going to emulate this network with the interface loopback 42. And we're going to put that in VRF 3344. And its IP address is going to be 151.42.1.1/24. All right, so we've got our VRF configured, 3344. and we've also got our ISP interconnect and our public IP block configured as well. And let's see. So we'll go ahead and do that on each customer edge router. So again, we're going to build VRF 3344, and our route distinguisher on the R2 is going to be 65,002 3344. And our route target is going to be 65,002 3344. Unspecified both. And our ISP interconnect, gig 00, sub interface 42. Its IP address is going to be 192.168.2.1/31. And then the public network that we're going to emulate on R2 is going to be New York. So its IP address is going to be 98.98.98.1/24. Right there. All right, looks good to me. Rinse and repeat this for router R3. Define our VRF, give it the route distinguisher. Router R3, our route distinguisher is going to be 65,003:3344. And our route target is going to be 65,003:3344. And our ISP interconnect, 00.42, encapsulation.1Q VLAN 42, and assign it to the VRF. Give the IP address 192.168.3.1/31. And we're going to emulate its network with the logical interface loopback 42. We're going to assign it to the VRF, and its address is going to be 24.137.88.1/24. So that looks good. So configure a VPRN service for the subscriber on each PE. Let's go ahead and get that out the way. We'll review it. Click. So just to review, what we're going to do is we're going to create the customer, then we're going to create the service, then we're going to configure our AD, RD, RT, and our router ID. Then we're going to configure our interface, then bind that interface, bind our SAP to that interface. Then we're going to configure the CE to PE protocol, and then we're going to bind our SDPs to the service. So first thing we do is create the customer, give them a description, subscriber C incorporated, contact admin@subc.com. Phone, I can't remember the area code. 1 second. All right. All right. Muted you by mistake. Or I hope I muted you by mistake. Hopefully I didn't cough in your ear. So this is our customer's configuration, customer 42. Of course, the customer ID is matching our VLAN ID. Next, we're going to create our VPRN service. So VPRN 3344, customer 42. So first thing we were going to do was configure our autonomous system number. Our autonomous system number, which was going to be 65,000. Then our route distinguisher, which was going to be 65,3344. Then our route target, VRF target, 65,3344. And just out of habit, I configure the router ID here as well, which is going to be the IP address for our CE to PE interconnect. So 192.168.1.0. So after we have our prelim info out the way, we can go ahead and create our interface. And it's going to be 2R1 VRF 3344. Create. And its address is going to be 192.168.1.0/31. Our router ID. And the SAP is going to be physical port 115 with the service delimiting VLAN tag of 42. So at this point, we should be able to activate this service via no shutdown and ping our CPE. So ping router 3344 192.168.1.1. So we've got layer 3 connectivity established between the PE and the customer edge. So we can go ahead and get our CE to PE protocol out the way. And again, we've chosen BGP. And we're going to put this in the group 2R1. Our peer AS is going to be 65,001. So these are going to be external BGP peers. So we're going to apply our policy statement MP BGP to BGP4 and configure our neighbor 192.168.1.1 no shutdown. And last but not least, we're going to bind our service distribution points to router N6 and to router N7 to this particular VPRN with the command spoke SDP 17006 create. Give it a description as well to N6. And from an operating system perspective, just like when you were creating a VPLS, you didn't have to specify a number after this colon. These spoke SDPs are the same way for a VPRN. The system automatically knows that this is always going to be a part of service 3344. So instead of asking you for a virtual circuit ID and a service ID, you only have to input the virtual circuit ID. It's smart enough to understand that this is going to be configured under service 3344, so it'll apply that as needed. But spoke SDP 17007 create, and we'll give this the description as well to router N7. And here's the configuration for router N1 for our VPRN. Let's go ahead and save that. 5 minutes. Okay. Once again, there's a configuration. Now we're going to go ahead and do the same for routers N6 and N7. But we're going to do it considerably quickly. So configure service, customer 42, our VPRN, autonomous system number 65,000, our route distinguisher 65,000-3344, our route target 65,000-3344, and our router ID, which is going to be the IP address of our near-in CE interconnect. All right, so we've got our prelim out the way, so let's get our interface created. Interface to R2, VRF 3344 create. Our address is going to be 192.168.2.0/31, and we're going to bind it to the SAT physical port 115 with a service delimiting VLAN tag of 42. All right, and let's test the layer 3 connectivity in New York between our PE and CE. The ping router 3344, 192.168.2.1. This layer 3 connectivity is working as well. So now we create or configure our CE to PE protocol. That's going to be BGP. We're going to put in the group 2R2. And our peer AS is going to be 65,002. So this is going to be an external peering. And our neighbor 192.168.2.1. We're also going to apply our export policy. Then finally, we're going to bind our SDPs. So our SDP from router N6 to router N1. Then our SDP from router N6 to router N7. Save that. Oops. Sorry about that. All right, that's going to be our config for on router N6. And now let's set it up on router N7. Create our VPRN, customer 42. Autonomous system is going to be 65,000. Router ID 192.168.3.0. Route distinguisher is going to be 65,000-3344. And our route target is going to be 65,000-3344 as well. Then we're going to create our logical router interface to R3 VRF 3344. IP address 192.168.3.0/31. And we're going to bind our SAP to it. All right, now let's test our layer 3 connectivity. Ping router 3344.192.168.3.1. So we've got layer 2 connectivity between the CE and the PE in Dallas. So let's go ahead and configure our CE to PE or PE to CE routing protocol. So in our case, of course, it's going to be BGP. Our peer AS is going to be 65,003. Our neighbor 192.168.3.1. And our export policy is going to be applied as well. That's what our config is going to look like on router N7. It's router N6 and router N1. All right, so we have the, let's verify this stuff. So VPRN 3344, show service ID 3344, do a base. I mean, but we're admin up, opera up, and we have layer 3 connectivity. And we've got our SDPs. Like I said, it's the SDP ID : service ID, but that's automatically inserted for you. But as you can see, we've got our route distinguisher for our VPRN. Let's do all. These are SDP to router N6. It's using MPLS as it's supposed to. And our SDP to router N7. Admin up, opera up. Using LDP signaled label switched paths. And then our SAP, of course. Got some statistics, packets in, packets out. And our logical router interface for the VPRN. Quite a few details. Alright, so on router N6, show service using. And in an earlier video, we had, I remember use these commands to verify these services. So let's, I guess let's run through a couple of these OAM commands. Our local SDP would be 17001, and our remote one would be 17006. Is that not how that works? I guess that's how that works. All right, so a request sent, a reply was received. So our services should be working. Let's do that from router N1 to N7. So remote SDP this time. Responder SDP ID unknown. Blank. Founder SDP ID unknown. Local. Did N6 give us that error? No, it didn't. Hmm. So what's going on here? Let's look at our SDP. Admin up, upper up. Yeah. So we have a service even built. Well, we have a service built, but we're missing our ever important spoke SDP. So this explains why no ingress and egress labels were being signaled, because we forgot uh, we forgot to bind the SDPs to our service. So um, configure service VPRN 3344 on router N7, spoke SDP 17001 create, and this is going to be the SDP to router, or the pseudo wire technically, or I should say the service tunnel to router N1, and then spoke SDP 17006 create description. This is going to be the service tunnel to router N6. All right, so now let's rerun that same command where we got the weird output. So when we ran this command earlier, you see we're getting all these NAs. Let's run that same command. And now we've got good data. All right, so that takes care of the VPRN service for the subscribers on each PE. Let's see how much time we have. 10 minutes. Oh, that is not a lot of time. So what we'll do is we'll just go ahead and save our configs on our PEs, and we're going to reboot these routers. All right, let's see how we're doing. The N1 looks good. N2 looks good. N3 is not happy. N4 is not happy. Well, they are happy. They just took their sweet time. N6 is happy. N7 is happy. So while these routers are booting, I will be back in a few minutes. So stand by for me. Thank you. All right, I'm back, and it looks like all of our routers have booted back up as well. So we'll just make sure we can reach router N7 and router N6. All right, let's do router N7 one more time. Okay, let's take a look at our VPRN, make sure it's still up, and our SDPs. It's like the 1-2 router N6 is up or down for some reason. So I think there's an OAM command to test that. There's SDP ping. Oh, so it can only ping if the SDP is up. That makes sense. Let's see. The service SDP. All right, so our transport tunnel is down apparently, which means that we have a router and interface that is not happy. Do an LSP ping N6. Let's take a look at our alpha. We don't have a label for router N6's forwarding equivalence class. That explains why MPLS is broken, or our transport tunnel is down. So now let's take a look at our label information base. It looks like we have them for all except router N6. So this might be a bit of a problem child. Let's see, let's check router N5's label information base. We do not have one for router N6. So there might be something going on with LDP on router N6. So let's take a look. We don't have, I mean, we have 2 targeted peerings, but we should have 2 link peerings as well. For example, if you look at router R5, we should have 1 link peering, sorry, to router R5. But yeah, this is strange. Router 5 sees it. However, router 6 does not. Let's try bouncing. Let's try bouncing LDP on the interface first. Oops. Still not seeing that link session. That is extremely weird. Now it doesn't see the, now router N5 doesn't see the session. All right, so we're gonna have to just do some little bit of ad hoc troubleshooting. Let's see, show router LDP session, router LDP interface. So they claim to be Opera up. I mean, service labels are being taken fine, but the link LDP labels are not. So let's do a little bit of debugging. So what we'll do is we will set up, or we have set up from the beginning of our videos, log file 66 for our debugs. So we're just going to be using that. Is there anything in 66? Nope. Okay, good. So let's debug router LDP interface 2 and 5. Messages. Show router status, just to make sure. LDP is up. Trigger router. I'm gonna bounce LDP. Hopefully we see some label mapping messages. All right. So we're sending hellos. That's always a good thing. Sending hellos. Are we receiving hellos? I don't see any hellos being sent out our interface on router N5. They're definitely coming out the interface from router N6, but I don't see them egressing router N5. No messages sent, one message received. So like, why isn't it sending messages? Let's try bouncing the interface. Okay, so sometimes it's as simple as bouncing an interface. But anyway, where there's no telling where we were. Um, I think we were okay. So we were verifying the VPRN service on each provider edge router, and we came across that strange scenario. So let's just make sure our service distribution points are all up. And they are perfect. So next is going to be our PE to PE routing. And we're going to be configuring a full mesh of multi-protocol BGP neighborships between the PEs. So let's review our config. So first we're going to set our autonomous system. Then under the BGP group, multi-protocol BGP peers, we're going to specify the family VPN IPv4, our peer AS, which is going to be the same as our local AS, and both of our neighbors, which from router N1's perspective is going to be router N6 and N7. So configure router, autonomous system arbitrarily chosen is 7029. I'm going to create the group multi-protocol BGP peers. Specify our peer AS 7029. So this is going to be an external neighborship. Neighbor N6's system address no shutdown. Neighbor N7's system address no shutdown. And that's our multi-protocol BGP config. So go ahead and save that on N1 and do the same for routers N6 and N7. So configure router, autonomous system 7029, BGP group, multi-protocol BGP peers. Our peer AS is going to be 7029. And our neighbors on router N6 is going to be router N1 and router N7. And last but not least, we've got router N7. So configure router, autonomous system 7029, BGP group, multi-protocol BGP peers. Our peer AS is going to be 7029. On router N7, our neighbor is going to be router N1 and router N6. And we're going to go ahead and save that config. All right. So let's you know what we should do also? We should be doing some debugging so that we can see this in action. But we'll save that. So let's see. I think we've configured the full mesh. Let's see. Show router BGP summary. Do we have a stat already established everywhere? Yes, but we were established using the wrong address family. So let's go back into router BGP. And this should be a one-liner. Family VPN IPv4. Just so that you can see all the address families that are available for multi-protocol BGP. But we're just going to be using the VPN IPv4. All right, so we're going to do that on all of our provider edge routers. And this time we should have, okay, VPN IPv4 peerings to each provider edge router. But of course, we aren't receiving any routes at this moment. Well, technically we are. And this is, I think, this is one of my pet peeves about SROS is that you can't view the the BGP rib out table. So it makes troubleshooting a bit, I wouldn't say complicated, but it's not something that I'm used to. I'm used to being able to see the rib out table or which routes are originating from this particular PE. That isn't possible unless the routes are being advertised. So what you're really looking at isn't the rib out table, rather it's the adjacent rib out table. If you do like a show router BGP neighbor advertised routes. Yeah, I'm trying to think if this would be a good time to go over debugging. Mm, no, we'll do it after our verification because we're pretty much done at this point anyway. So we could do it after the verification. So let's first confirm. Oh, and by the way, our PE to CE routing, well, our PE to PE routing. First of all, we've got that out the way. We've got VPN IPv4 neighborships to between each of our PE routers. So our PE to CE routing Configure each CE to distribute a public IPv4 system address to the PE via eBGP. All right. So okay, so we have no BGP config yet. Okay, so on router R1, our BGP AS is going to be 65,001. And we're going to be configuring this neighborship under the VRF 3344. So first we're going to make sure that we redistribute our network. And on R1, our network is going to be Los Angeles, so 151.42.1.0 with a mask of /24. Then we're going to configure our neighbor, 192.168.1.1 with the remote AS of 65,000. Cannot configure local system as neighbor. Oh, my apologies. Neighbor 192.168.1.0, remote AS 65,000. Let's go ahead and write those changes. And we're going to do that on all of our CPEs. On router R2, our AS is going to be 65,002. Again, the VRF 3344. Our network in New York is going to be 98.98.98.0 with a mask of /24. And we're going to specify our neighbor 192.168.2.0. The remote AS is 65,000. We're going to do the same on R3. Our local AS is going to be 65,003. Build our neighborship under the VRF 3344. And our network in Dallas is going to be 24.137.88.0 with a mask of /24. And our neighbor 192.168.3.0. We want to specify the remote AS of 65,000. All right, so we see that we have a new BGP for neighborship to the ISP from our customer edge on router R3, the same on R2, and the same on R1. And by using our network statement, for example, network 151.42.1.0 mask /24, we've created a policy to distribute the public /24 to the PE router via our external BGP neighborship. And we've already taken care of the last step here, which is configure VPRN service for the subscriber on each PE. So we can move into the verification. So we'll verify this left to right. If you've downloaded this presentation, you could like and you have this open in a separate PowerPoint window, you can go ahead and pause, well, not pause the presentation, but open your PowerPoint and just go to this slide and snap it to the left or snap it to the right. But we're going to be verifying from left to right here. All right, so first we're going to confirm the IPv4 prefixes are being distributed from the customer edge to the provider edge. So let's do show BGP ref 3344, leave all. Okay, that's what I wanted. So show BGP VRF 3344, all neighbors 192.168.1.0 advertised routes. We're able to verify that we are advertising our public /24 to the PE router along with our route distinguisher. So we can hop in the PE router N1 and verify that we are receiving those routes. Two ways, show router 3344, BGP neighbor 192.168.1.1, received routes. So we're receiving our /24. Or we can just look at the routing table. But anyway, show router 3344 route table. So yeah, we're receiving that route via BGP. All right, so we've confirmed that the IPv4 prefixes are being distributed from the CE to the PE, and that the PE is accepting those prefixes. So next, let's confirm that the IPv4 prefixes are being converted into VPNv4 prefixes by the provider edge router. So when BGP labeled unicast generates a label, a VPN label for the prefix, and places this prefix in the VPN table, it's going to have that route distinguisher pre-pended to it. So that'll make the, well, just show you. So show router BGP. Oh, brain fart. Show router BGP routes. Christ. Family VPN v4. So back to my point earlier, how I was saying that the route table that you see doesn't show the routes you originate. In order to see the routes you originate, or in order to accomplish our verification here, which is to verify that the IPv4 prefix is being converted into a VPNv4 prefix, we're going to have to take a look at the routes that are being advertised to our neighbors N6 and N7. So if we do show router BGP, neighbor, and router N6, advertised routes, VPN IPv4, you see that we have our prefix from, well, our Los Angeles prefix, along with our route distinguisher, as well as our VPN label. And see, I'm trying to remember exactly how we can look at the information that this router would send in an update message. So router BGP routes. Okay, so that's the way to look at our adjacent rib out. Show router BGP routes, VPN IPv4, that's the family, and then the IPv4 prefix, and we specify the hunt keyword. And we can see this is what's going to be sent in an update message to our neighbors, which is our route distinguisher, our prefix, our VPN label, as well as our route target. Let's go back to the PowerPoint. This PE to PE update message is what we're looking at right now. So just to go back, we have our route distinguisher 65,000:3344. We have our route target 151, I'm sorry, our IPv4 prefix 151.42.1.0/24. Our VPN label, which is 13.10.70. And our route target, which is 65,000:3344. So by looking at our routing table and specifying the hunt keyword, one second. Excuse me. We're able to examine the attributes that'll be in our BGP update message that's sent to our neighbors. All right, so we've confirmed by looking in, by specifying that hunt keyword and looking in our adjacent rib out table that the IPv4 prefixes are being converted into VPN v4 prefixes by the provider edge router. Just one more time. Here's our /24. Here's our VPN v4 prefix version of our /24. Again, with our route distinguisher that's prepended to our IPv4 prefix and our important VPN label that represents our IPv4 prefix. All right, so next, confirm VPN v4 prefixes are being redistributed to each PE with the appropriate route distinguisher. Well, it's not going to be difficult to do. We're just going to look at the advertised routes to each of our multi-protocol BGP neighbors. So show router BGP neighbor, router N6, advertised routes, the family VPN IPv4. So we see that router N1 is advertising the route that, based on our AS path, is being originated from 65,001, which is Los Angeles. And let's run that same command, but for router N7. So show router BGP neighbor, all sevens, advertised routes, VPN IPv4. You can see that the route is being advertised to router N7 as well. And that's with the appropriate route distinguisher. All right, next, confirm VPN v4 prefixes are being converted back into IPv4 prefixes and redistributed from the PEs to the CEs. So we've confirmed by looking at the routes being advertised to router N6 that we're sending this prefix, or we're sending the update message that contains this IPv4 prefix. So we want to make sure on router N6 that the PE router is not only accepting the routes, but also installing those routes. And lastly, redistributing those routes from the VRF to the customer edge router. So we verified on router N1 that we were advertising the routes. Now let's verify on router N6 that we're receiving the routes. So show router BGP, neighbor, router N1, received routes, VPN IPv4. And sure enough, we are receiving the route along with the route distinguisher, the AS path, uh, and the VPN label. So now let's take a look at this. Let's take a look at our BGP routing table. I'm sorry about that. I had to step away for a second. So we're looking at the our BGP adjacent rib in table on router N6 that contains the update message that we received from router N1. So we see it contains our prefix, which is a /24 network that represents Los Angeles. It's got the appropriate next hop of router N1, the route distinguisher and the VPN label, as well as the route target and AS path. So based on the route target, well, first of all, based on the VPN label, the router is going to understand that this is the network that that we're going to be dealing with, and then based on this route target, uh, the router is going to allow this network into the VRF or the VPRN that corresponds to this route target. In our case, this excuse me, this packet came in on VPRN 3344, so it's going to egress VPRN 3344 as well. All right, so let's see. All right, so in order to verify that, we're just going to look at our VPRN's routing table. We could do that. So we can see that this route is successfully being converted from a VPNv4 prefix, which we have up here, 65,000:3344, our IPv4 prefix, into a regular IPv4 prefix and being installed uh, in this VPRN's routing table. Okay, last we're going to make sure it's being redistributed from the PEs to the CEs. So we can do show router 3344 BGP neighbor, and on router N6, our neighbor is going to be 192.168.2.1 advertised routes. So you see that, yes, we are indeed advertising Los Angeles as well as Dallas. So now let's hop into the customer edge or our New York site, and we could verify that these routes are being received. Show BGP VRF 3344. All neighbors 192.168.2.0. Received routes. Hmm. All right. Well, I guess that's the method we'll have to use. So uh, we can see that we are receiving uh, a prefix for Los Angeles as well as a prefix for Dallas with the next hop of router N6. And based on our AS path, we know 65,003 is Dallas and 65,001 is Los Angeles. So that's correct as well. So last, we will confirm reachability between all CEs, pinging and sourcing only the public IPv4 system addresses. So this is what's going to uh, really prove whether or not we've interconnected all three of these separate broadcast domains into a single routing domain. So if we're in New York, our New York router, and we want to ping Los Angeles, which is 151.42.1.1, we're going to source it with our own system address. Try that out and see that the pings are successful. Now we can repeat that with Dallas. So if we ping Dallas, sourcing New York, you see that those pings are successful as well. Now let's do it on the other router. So we're going to hop in our LA router and we're going to ping New York from Dallas. That's successful. I mean, ping New York from LA, I'm sorry. And now we're going to ping Dallas from LA. And that was successful as well. Last but not least, let's do this from Dallas. We're going to ping LA from Dallas, 51.42.1.1. We want to source it with our local loopback 42 address. And that's successful. And now we're going to ping from Dallas to New York. And that was successful as well. So just look at the routing table. So in Dallas, we are receiving New York and Los Angeles via BGP. In New York, we are receiving Dallas and Los Angeles via BGP. And in Los Angeles, we are receiving New York and Dallas via BGP. And of course, we have interconnectivity through all three of the broadcast domains. So that essentially means that we've accomplished our task of allowing all three of these subscribers' broadcast domains, the 151 network in LA, the 24 network in Dallas, and the 98 network in New York, to be able to reach each other, or we've interconnected them, or we've provided a way for these three broadcast domains to route traffic in between themselves. So our VPRN is successful at this point. What we'll do is we'll do some debugging. I'm going to save the configs on this, but we'll do some debugging so we could look at the packets as their label switched across the IP MPLS core. All right, so first what we're going to do is we're going to shut down the VPRN service on router N1 as well as multi-protocol BGP. So we've got inside a log 66. Router N1. Okay, we don't have anything good. So what we'll do is we're going to debug this on the router, and also we're going to perform some packet captures so that we can see like the label stacks and whatnot. So let's debug. Let's debug router 3344. Let's debug these update messages. And let's also debug router BGP update messages for multi-protocol BGP. And let's do RTM as well, and route refresh. All right, so let's do a shell debug. So we're debugging route refresh, the route table manager, and any update messages for our CE to PE peering and for our PE to PE peering as well. You know what? Why don't we debug it over here also? I'm just turning that LDP debugging off. All right, that looks much better. So now let's sort of we're going to follow the life of this /24 network. life of this guy. All right, so first we see that this network is configured on the interface loopback 42. And we also see that this network is a part of VRF 3344. So if we look at VRF 3344's configuration, we see this route, this VRF has a route distinguisher of 65,001:3344 and a route target of 65,001:3344 as well. And this customer edge router R1 is paired with our PE router, router N1. There's a better one. So R1, represented by C, is paired with router N1. And because of this command network, router R1 or subscriber C is going to send this prefix in an update message to router N1, or it's going to distribute that route to its local PE router. So let's see what happens when N1 gets that route. So we're going to reactivate the service VPRN 3344. All right, so we see that once we activated the service, uh, our VPRN, the route table manager, did add this IPv4 route to our VPRN's routing table via BGP. So we see the update that was received. We've got our 151 network in this update. And after our router received that update, you can see that it added the IPv4 route with the route table manager. So if we look in our route table, you see that sure enough, we have our 151 route that was within our update message that came from the customer edge. All right, so now what happens when that 151 route makes it from the customer edge router into our VRF and multi-protocol BGP is enabled uh, along with the VPN v4 address family. Let's go ahead and activate BGP. Let's see what happens. So when we activated multi-protocol BGP, you see that our VPN v4 prefix was added to bases like global. So this means global. So it was added to a global BGP table, that being our VPN v4 table. So our VPN v4 prefix was taken out of VPRN 3344, prepended with the route distinguisher, and added to our VPN, our BGP VPN table with the route table manager. And what happens after that route is added with the route table manager? Well, then a peering gets established. A multi-protocol BGP peering is established between router N1 and N6. So router N1 sends router N6 an update message that contains the route distinguisher, the VPN label, the IPv4 prefix that VPN label corresponds to, as well as the route target that dictates the VPRN that the IPv4 prefix belongs to. So if we take a look at our update message that was sent to router N6 from router N1, again, we have our address family, which is VPN IPv4 or AFI1 SAFI 128, our next hop of router N1. But more importantly, we have our route distinguisher, 65,000 colon 3344 that distinguishes this route in our network. We have our IPv4 prefix, which is what we redistributed from our customer edge router in Los Angeles to our local PE router N1. This guy right here. And again, these two values together form our VPN-v4 prefix. We also have our VPN label, and our router generated the label 131070. In our example, it was the label 3344. And again, this VPN label is going to correspond to an IPv4 prefix. And our update message contains our route target in the form of a BGP extended community, 65,000 colon 3344, as we can see here. So this update message is sent from router N1 to router N6. And let's see if router N6 has received it. All right. And you can see router N6 does receive this BGP update message. And again, it contains our IPv4 prefix, our route distinguisher, our VPN label, as well as our route target in the form of a BGP extended community. And after router N6 receives this update, it processes the update, then adds that VPN-v4 prefix to its own VPN BGP VPN table with the route table manager. So router N6 receives an update from router N1, processes that update, and then installs or adds that VPN-v4 prefix into the BGP VPN table with the route table manager. And it also receives, not only does it receive that public /24 in an update message, but it also receives the private interconnect, that private interconnect for the eBGP peering through an update message as well. So that 192.168.1.0 and .1 network, that's in an update message as well. And as you can see, it adds both of those VPN-v4 prefixes to the BGP VPN table. And it looks like router N6 has rebooted. I guess they all decided to reboot. Okay, well, I guess we will just resume whenever these routers come back online. So stand by for me, please. All right, so we're just waiting on router N6 here. All right, and we should be good to go. So we've got our neighborship to N7 up and our neighborship to N1. And our neighborship to N6 should be coming up once this protocol converges. But let's get back in here and re-enable those debug commands. See. All right, so let's just do this again. We're going to shut down the VPRN service on router N1, as well as multi-protocol BGP. Clear the log on router N6, and then we're just going to enable our service. And re-enable our multi-protocol BGP session. All right, so let's take a look at what router N6 strange, it didn't record anything. Let's shut down the service on router router N6. Okay. All right, so now we're right back where we were from. So as we can see again, router N1 has sent an update message for the private ISP interconnect between itself and the Los Angeles site. And router N6 has added that VPN v4 prefix to its BGP VPN table via the route table manager. Router N1 has also sent an update message with Los Angeles with their public/24, and again it's also installed it in its BGP VPN table as a VPN v4 prefix with the route table manager. So let's take a look at the BGP VPN table. And sure enough, we do see our VPN v4 prefix. Now, based on the route target, that's going to dictate whether or not these routes, the route distinguisher 65,000, the 151, and the 192, well, really any of these routes is going to determine which of those gets redistributed or not. So let's take a look at the VPRN's routing table, show router 3344 route table. And we see that based on our route target, we do have Los Angeles, their public /24 installed in our route table, as well as the ISP interconnect. And we have Dallas's public /24, as well as its ISP interconnect installed in our route table as well. So now we can verify or speak about the routes being redistributed from the provider edge router to the customer edge router. So we can verify our our PE to CE routing at this point. So as you remember previously, if we go into the service context for VPRN 3344, we have an export policy applied. Okay, so let's just take a look at that policy again. All right, and let's take a look at our routing table. All right, so just the VPN routes and our routing policy. So our routing policy is saying accept routes into the BGP table from the BGP VPN table. So what our policy is doing is it's taking all of these routes, the /24, /24, /31, /31, and installing them into the BGP table, which is show route table, protocol BGP. Okay, much better. So I'm sorry, this is our adjacent ribbon table. So it's not going to be installing these routes into the routing table. Instead, these routes are going to be found in our adjacent rib out table. So if we look at the routes that we're sending toward our customer edge, or the routes in the adjacent rib out table, then we should see all four of these networks. So show router 3344 BGP neighbor 192. There we go. Advertised routes. Now instead of seeing 4 prefixes, we're only seeing 2. And why is that? If you go back to our policy references the prefix list VPRN 3344 sites. Let's see if I can just show just that prefix list. Okay, cool. So these are the only prefixes that are going to be allowed to be redistributed to our neighbor. So since our private interconnects are not in this prefix list, only our public /24s, then those are the only networks that are going to be advertised to our customer edge router. So if we and we'll have to sift through. We could probably key in on VPRN 99. Let's see. 3344. I'm sorry. Application. Oh, router. That should be it. No, I guess it's not it. All right, we'll just do it the old-fashioned way. All right. So now I'm just trying to see all of the updates that are associated with our VPRN 3344. And here we see that we received an update from our CPE in New York with its /24 network. And right after we received that update, you can see that our route table manager added the IPv4 prefix to our VRFs routing table. And that's an update that's being received from, well, one thing you can also note is that right after our PE router added this route to the VPRN's route table as an IPv4 route, our PE router also added this route as a VPNv4 route to the BGP VPN table, route table manager. So you can look at the timestamp. It's literally the same time. So let's look at the interactions with our private peering. All right, so this is when our provider edge N6 sends an update to our New York customer edge with the IPv4 prefix of Dallas. And here's what we were looking for. Here's the update it sent with the IPv4 prefix for Los Angeles. You see it has its AS path, extended community, also a next hop. So you can hop into R1 and verify if that update was received and if the route was installed or not just by looking at the routing table. And you see, yes, we do have. I'm looking at the wrong. I'm asking myself, why is it showing up as a locally connected route? All right, so we were in Los Angeles. I'm sorry, where the route originates. But R2 now we're in the New York CPE. So if you take a look at R2's route table, we're receiving the Los Angeles route via BGP. And I believe that we've gone through all the BGP commands, but we'll just do it again. So here's our Los Angeles network /24, along with the next hop of our PE router and an AS path, which is our service provider, and then our CPE in Los Angeles. So that should just about do it. We followed the life of the packet from its original interface in Los Angeles uh, through its VRF and through its BGP v4 neighborship and its redistribution with the provider edge router N1. And we've also seen that N1 received this prefix from the customer edge in an update message and added that IPv4 prefix to the VPRN's routing table. And then afterward, we see that through BGP labeled unicast and multi-protocol BGP, uh, that IPv4 prefix was prepended with a route distinguisher, and the VPN v4 prefix was added to the BGP VPN table. And then that VPN v4 prefix in an update message was sent from router N1 to router N6. And we examined uh, when we saw the BGP update from router N1 and router N6 right here, that contains the public /24 for Los Angeles, as well as the route distinguisher, the VPN label, and the route target. For the route table, do the command show router 3344, route table protocol, BGP, VPN. All right. So we also saw where the route was being installed into the BGP VPN table. And through our policy, and by debugging our private interconnect, we saw where the VPN v4 prefix was sent to its neighbor with the next hop of self and an update message for what it's worth. And then inside of the New York router, we saw that N6 was successfully redistributing that /24 over its eBGP peering, and the New York router is in fact accepting that /24 and installing it, and the New York site is reachable from Los Angeles, and the Los Angeles site is reachable from New York. So that's the life of this particular network, this particular public /24. That process repeats for each site's public network, and that's pretty much the surface of the basics of how a VPRN or a layer 3 VPN or an MPLS VPN operates. Now, just before we go, just the last thing that I'd like to do is just do some debugging, just some packet captures, so that we can see the label switching in action. And this won't take long at all. All right, so we're going to debug the circuit between R1 and switch 1, as well as the circuit between N3 and N4. So an access circuit and a core circuit. Now let's just throw some pings here. We're going to ping New York from Dallas. Repeat that 50 times. All right, we can stop our packet captures. All right, so let's just take a look at a packet that left our CPE. So we can see it's an ICMP packet, and it's got a source and a destination address. Our source being Los Angeles 151.42.1.1, and our destination being New York 98.98.98.1, and it's encapsulated with a VLAN of 42. And notice the source MAC address and the destination MAC address as well. So now let's take a look at the ICMP packet from within our core. All right. So we see that with this particular packet, again, we have the same original packet, which was being an ICMP packet, the same source and destination, Los Angeles and New York, also the same source and destination MAC address. The only thing that's different is that we now have a label stack that's inserted in between the layer 3 and the layer 2 headers. Sorry, the layer 3 IP header and the layer 2 data link header. So our service label is 131066, and our transport label is 131065. So what we would expect is our service label 131066 to be the VPN label that BGP label unicast has generated to represent this particular prefix 98.98.98.1, and the transport label 131065 just to be the outermost label that router N3 or pushes or swaps or pushes on top of this particular datagram destined for a particular forwarding equivalence class. So the first thing we'll do is let's hop in router N1. Too many things open. All right, so show router, BGP routes, and we should be able to just type that. Okay, awesome. So we can see that our label is, oh, beautiful. I close it. Let's open it back up. Let's see some more pings. Okay. So our service label, we were saying that this is our VPN label that the PEs have agreed upon, that BGP labeled unicast generated, and that the PEs have agreed upon to represent this particular prefix 98.98.98.0/24. So we can take a look in our ingress label edge router and look at that prefix in our BGP VPN table and verify that yes, the VPN label uh, is 131066. VPN label 131066. Label 131066. So now the transport label of 131065 and another thing that we can say also is uh, we have to sort of prove that LDP isn't generating the service labels for our VPRN. So if we were to take this label of 131066 and look in our label information base, which is the database that LDP manages uh, and generates labels for, show router LDP bindings, we see that 131066 is actually the label that N1 uses, the LDP label, I'm sorry, that N1 uses to represent router N5. So you should you should be asking yourself, how can 131066 or you should be asking yourself if BGP labeled unicast, say I'm just lying to you and BGP labeled unicast doesn't generate the label and something else is happening. You should be asking yourself, if LDP really does generate this label and BGP labeled unicast does not, then how is it that the routers know what to do? The label switched routers know what to do when they receive a packet with a label of 131066. And the answer is they know what to do with it because LDP doesn't generate that label for this particular prefix. That operation is handled by BGP labeled unicast, which has its own database, which is nothing. I mean, I'm sure it's similar to a label information base, but it's two completely separate things. So let's just take a look at the label information base. Well, the label forwarding information base. And we have several operations here for 131066. So one of the operations is if no label is, if traffic is not labeled, period, then push a 131066 on top of it. Or if traffic has an incoming label of 131065, then push a 131066 on top of it. So that's the LDP operation for the label 131066. The BGP labeled unicast operation for a label of 131066 is to place this in a VPRN whose route target is 65,033.44. So we had a transport label of 131065, I believe. Yep. So I shouldn't have scrolled all the way down. I was going to say, so then we should expect then that our LDP operation for a transport label of 131065 should be a push operation, and it should be egress out of our interface connecting to N2. And we also have a swap operation of 13. 1061. Um, but again, the main thing we're looking at here is from router N1's perspective, it's supposed to push this label of 13.10.6.5 on top of this traffic. Now, this packet came from between router N3 and N4, so let's check router N3's label forwarding information base. Well, what I'll do is I'll check the forwarding equivalence class for router N6's system address, and we'll compare that to the label that's in the LFIB for what operation we should perform if the label is 13.10.6.5. So show router LDP, bindings active, prefixes prefix, router N6, and what do you know? If traffic is destined for router N6 and it has no label on it, then router N3 is to push a label of 13.10.6.5 and then egress it out of this interface toward this next hop. And if traffic has an incoming label or has a transport label of 13.10.6.5, then router N3 is to swap that for 13.10.6.5 and forward it out this egress interface again toward router N4. So that takes care of the VPRN video. Let's see if we captured any update messages. I mean, there's one more thing we can do. We could look at a BGP update message in Wireshark. Which is what we'll do. Why not? Done everything else, but why not do this one thing? Let's go ahead and stop these captures. And let's capture, well, first let's shut off BGP. And let's capture between router N5 and N6. And again, all we're going to be doing is catching the, looking for the BGP update messages, sourced from router N1 and destined to router N6. Now let's reactivate BGP. Took long enough. All right, so we've got our update messages. I should save that config. So let's take a look at our update message from router N1 to router N6. Now, first thing to notice here is that since this multi-protocol BGP session is built through our service tunnel or through our targeted LDP session, in order to exchange label information, router N1 and N6, from that particular perspective, believe that they're directly connected. So our source is going to be router N1 and our destination is going to be router N6. But that traffic is being tunneled through our service distribution point from PE to PE. So let's take a look at our update. In our first BGP update message, in the path attributes, we have the multi-protocol multi-protocol reachability network layer information. And let's expand that. And we have our next hop of router N1. And for our NLRI, we have our prefix, which is the ISP interconnect, our route distinguisher 65,000-3344, as well as our VPN label 13170. So if we go to router N1 and we look in our VPN v4 table for our private ISP interconnect, so you have the service label, or the VPN label, I'm sorry, 13170. All right. And then we have these other attributes, AS path, local preference, etc., etc. Now let's look at our other update message, the multi-protocol reachability network layer information attribute. Next hop is router N1. And again, we have our NLRI for our prefix for Los Angeles, 151.42.1.0, with the route distinguisher of 65,000:3344, and our AS path. And of course, I didn't show this in the other one, but our extended communities. So our route target, it's a transitive 2-octet AS specific route target. So you can see our 2-octet autonomous system, 65,000, our 4-octet assigned number, 3344. And we'll just look at the other BGP update. So those extended communities are the same as well. So we could also verify the VPN label of our Los Angeles network. 13.10.70. So 151.42.1.0. So router BGP routes VPN v4 151.42.1.0/24 detail. And sure enough, our VPN label of 1310.70. So we can see that BGP labeled unicast is generating VPN labels for these prefixes. The route distinguisher is being prepended to the IPv4 prefix. The VPN v4 prefixes are being redistributed and installed by the provider edge routers. And those VPN v4 prefixes are being converted back into IPv4 prefixes and installed into the appropriate VPRN via the BGP extended community or the route target. So at this point, I would consider our lab a success. We've proven that the subscriber broadcast domains in Los Angeles, Dallas, and New York are interconnected and can route between each other. So the next video is going to be an IES video. I have no idea how long it's going to take to put out, but thank you for being patient. I really hope you enjoyed this VPRN video. As always, if there is anything I can do to improve the quality of these videos or any specific topics, any misinformation, any mistakes in my presentation, please let me know. My LinkedIn as well as my email address will be in the video's description, as well as a link to download this presentation. So I hope you all enjoyed it. Thank you and have a great day.